Let's take a look at the general form of a vector error correction model, a VECM. And that is alpha times beta times z1 plus psi z2 plus vt. Now, notice this part here. This is your long run dynamics. Okay? And our efforts are going to be to figure out what alpha and beta are. Now, what Johansen figured out is that instead of formulating a log likelihood of this expression and sending it to the optimizer, he figured out a shortcut. What he figured out is the fact that you can formulate the following eigenvalue problem. S11 minus S10, S00 minus 1, S01. You could solve this, and this would also maximize the log likelihood. Okay, so the key advantage of the Johansen procedure when fitting VECMs is that you don't need to send the log likelihood to the optimizer. You can simply send it, you can simply apply a series of, roughly speaking, 6 steps to figure out the weights on alpha and beta. So it's much more computationally efficient to do this. Okay, so let's take a look at our core function. Now, here I have the Johansson function right here. It implements the core of the Johansen procedure. It takes 3 arguments. The first argument here, y, is a matrix in levels. Okay, a matrix in levels. That's very important. It's not a difference matrix. This is a matrix in levels of vectors that are integrated of order 1. You cannot send in any vector that is stationary. If you send in a stationary vector in y, this procedure will solve for weird weights. Okay? The second argument here is lags. And this is the number of lags specified in the VECM model, how long of a memory you want the model to have, and the model itself. Now, Johansen specified 5 models right here: H2, H1 star, H1, H star, and H. And we will go over them. But first, we need to, let's start with preparing our inputs. Okay, so let's go to step 1. Step 1 is preparing the inputs. Now, we need a couple of inputs known as dy, z0, z1, z2. Okay, what is dy? dy simply differences the matrix, the level matrix. Okay, that's all it does. And that's dy. Z0, it trends the top of the matrix, the difference matrix by the lags. Okay, so dy and z0 are very similar. Now, z1 is important in that it's in levels. Notice that it is a matrix that is in levels. Z2 here is a wide matrix of differences. Okay, so you're taking the differenced matrix and essentially copying strips depending on how many lags you have here. So as an example, if I come down here and specify, let's say, lags of 6, okay, and it'll set the submatrix. So the width of this submatrix, 1 to lags minus 1, should be 30. Okay, so let's print this out. Print fn, z2, console system.console.read key. Let's run that. Notice that you get a wide matrix, 246 by 30. Now we have 5 variables, and the width of this matrix is now 30 right there, okay? So essentially, it's taking the difference matrix, dy, and copying strips of it, adjusting for the lags. Okay, that's all it's doing, creating a very wide matrix of lags. Let's go back to what we had. So those are the inputs. Those are pretty straightforward. Now let's look at the model blocks. The model blocks consist of modifying Z1 and Z2 depending on the Vecum specification. Okay, so what are the Vecum specifications? Johansen describes H2, H1 star, H1, H star, and H. Okay, he describes this in his paper. Now, the left-hand side here can be thought of as the data in levels, and the right side here are the data in differences, the wide matrix that we just looked at a second ago. Okay, so on the left-hand side, we have the matrix in levels, and the right-hand side, we have the difference, the wide difference matrix. And depending on the specification, according to his paper, so H2 is basically unmutated Z1 and Z2, which is what we return right there. We do not mutate Z1 and Z2, simply return them. H1 star, we append a constant, which is a column of ones right there, to Z1 and return that. We return Z2 unmutated. H1 is, we do not modify the levels data, but we modify the wide difference matrix by appending ones, a column of ones to it. H star consists of adding a trend to the levels. Okay, we add a trend to the levels right there, and adding a ones, a column of ones to Z2 right there. And the final model H, all we're doing is adding a constant and a trend to constant and a trend to the wide difference matrix. So once that is done, we've specified our Vecum specification. Now what we need to do is calculate the residuals. Okay. Now the residuals, what Johansen figured out is that you could use the sum of squares of this regression right here. Okay. You could use the sum of squares of this regression right there to you do an Eigen Decomposition and figure out what alpha and beta are. Now, what is this regression? Notice that this here, Z2 solves Z1, gives you the coefficients of Z2 against Z0. What is Z2? Z2 is the wide difference matrix. So you're regressing the wide difference matrix on Z0, which is the difference matrix. This is the narrow difference matrix. Okay, so you're taking the wide difference matrix Z2, regressing it on the narrow difference matrix Z0, and coming up with the coefficients for that, coming up with an estimate of Z2, and getting the residuals against Z0. Okay, which is the narrow difference matrix. Then you're doing the same thing, but you're doing it for Z1, which is the levels data. Okay, so you're getting the coefficients for a regression of Z2 against a wide difference matrix against the levels data, you're getting an estimate for Z2 and coming up with the residuals against Z1. Okay, and Z1 is trend. So you're coming up with, you're doing a series of regressions here. You're getting an estimate for Z2, and you're getting the residuals of Z1 against this Z2 estimate right there. This brings us to our next section, which is the sum of squares. Okay, so remember what we mentioned before, that Johansen figured out that the result of this calculation right here, solving for this eigenvalue problem, maximizes the log likelihood. And S11, S10, S00, S01 are the sum of squares of this regression that we just performed right here. Okay? And that's all this is. Notice R0 transpose times R0. And we're simply adjusted for the row counts of R0. And we're getting our sum of squares. Nothing complicated going on in this section right here. Okay? And this brings us to our key section, which is the Eigen Decomposition section. Okay? Now, the Eigen Decomposition boils down to, so this is, now we're on step 5. So this is step 5. The Eigen Decomposition boils down to this. This can also be thought of as taking, what is L? So L is, you're taking S11, negative half, S10, S00, S negative 1, S01, S11, negative 1 half transpose. Okay, so what is Cholesky? Cholesky is simply taking the square root of a matrix. Typically, you can think of it that way. So this is the calculation that we're doing. And this is the core of the Johansen methodology, solving this Eigen Decomposition. Okay, so look at S11 here. We're calculating the matrix square root, which is Cholesky factor. We're putting it in L. And then we are doing an inverse of L times S10, inverse of 00, times S1, transpose inverse of L, which is this calculation right there. Okay? And once we get that, we are essentially home free at this point. All we need to do is we need to sort the eigenvector matrix according to the magnitude of the eigenvalues. Okay? And once we do that, we get our estimates, our coefficients for the weights on the level data. Okay, this is our long-term dynamics. The final step is we need to standardize this coefficient, this set of coefficients here. So we standardize them by setting the first element of each set of weights to 1. Okay, once we standardize that, we get this standardized set of variables. We'll return that right here. And let's run this, and I'll show you what that looks like. So right there is, well, where did that go? So right there, we see our weights for the associated with the largest eigenvalue. So it's 1, 1.557, negative 1.557, negative 0.937, negative 2.216, 1.7409. Okay? Now, if we take this set of weights and we look at our core data set, so this is our core data set right here. Let's first plot this data set. So this is a time series in levels, okay, of a bunch of stock prices. Now, if we weight each of these by the weights that we just saw there, let's go ahead and do that. What we'll end up with is a stationary spread. So this will let us transform, copy that down, and this should be our stationary spread, which is the sum Now let's plot this. That spread is now stationary. So we've taken a set of stock prices in levels that were non-stationary, and we've combined that data set in a way that gives us this stationary spread. So in other words, we are capturing long-term dynamics with this set of weights. And that is Johansen Cointegration. Okay, so we've taken this data set in levels and we've turned that stationary by figuring out what the weights are on that data set. Okay, so that is Johansen Cointegration, and all it is actually less than 50 lines of core calculations. Okay, so preparing inputs, preparing model blocks, calculating residuals, calculating sum of squares, Cholesky plus Eigen Decomposition, and post-processing. That is it. That is how simple Johansen Cointegration is. But you know, again, the key insight that Johansen had is that you could avoid the optimization problem associated with the log likelihood and simply go through this series of steps, which is much faster to do, much less compute intensive, and get your answer that way. If you are interested in a commercial solution for Excel, we create software known as parietal numerics. And if you have the engine up and running here, like I have, what you can do is simply choose your region of interest. So choose your data set like that. Go to the parietal tab. Under Cointegration, click on Johansen. Select all the variables of interest. And let's go with model 3, which is what we had in that demo software. And if you look at, let's say, the eigenvectors associated with the largest eigenvalue, let's go ahead and copy this. And we'll get effectively the same results here. So let's do that. Let's transpose paste there. Let's standardize the weights. So you don't need to standardize the weights, but the result that you're going to get is going to be the same. So let's go ahead and do that. Standardize all these weights. And notice the weights here are the same that we got from our little script there. Now, the implementation of this in our software is different. This is a much more robust C++ implementation with a lot more metrics get returned. And it's just much more detailed, okay? So, but the Fsharp script that I just walked you through gives you the core understanding of what's going on behind the scenes. So if you're interested in an Excel-based solution, a commercial solution, we create software for this, as well as other econometric and statistical routines built in. And that pretty much does it. Thank you for watching.